All right, so let's do some review on flip-flops, because we're going to start talking about synthesis of state machines today, and that's going to also require that we're well versed with flip-flops. So that's warming up in a few seconds. But I'll start drawing. So all of our flip-flops have a clock input. Okay, sometimes it's not even drawn, but it should usually be drawn, and it's usually got that little triangle which tells us that this is an input that's triggered by a change rather than a level. Okay, so this is the edge triggered thing. So there's a typical D flip-flop. The clock is feeding in, it's positive edge triggered. One input D, one output Q. Again, we don't think of the clock as an input, even though it's going in. It's not the same as like a D or a J or a K. So one input, one output, and a truth-like table that's fairly straightforward. But there's a lot going on in this table, right? What this is saying, and let me change this to Q plus. What this is saying is that if D is 0, when the clock ticks, the new value of Q will be 0. If D is 1, when the clock ticks, the new value of Q will be 1. So this is Q after the clock ticks. Okay, so that's just a data flip-flop. It's useful for making things like registers where you have a whole bunch of numbers and you want to save them at some point in time. At that point in time, hit the flip-flop clock, all of those values get loaded in. SR, we don't really use. You're never going to see an SR from me on a test, probably. But we can do a picture anyway. So this is a set reset. So if R is 1, that's the reset condition. If S is 1, that's the set condition. If they're both 0, that says don't change the value of Q at all. Ignore your inputs. So the new value of Q is just Q, whatever the old value was. And for our purposes, if both of these are 1, the so-called forbidden state, we'll just say that resets it. Okay, the toggle flip-flop has a toggle input and has a Q output and the usual clock. So if T is 0, what's the output? What's the value of Q after the clock tick?
Q.
It's still Q, it doesn't change. And if T is 1, Q bar toggles. And then the best flip-flop of all is the JK. And it starts off like an SR. 0, 0 doesn't do anything. 0, 1 resets, 1, 0 sets, but then 1, 1 acts like a toggle. And so the new value of Q will be the opposite of the old value, the complement. And if you see a flip-flop and there's a circle out here by the clock, that's negative edge triggered. We imagine it as saying the clock is getting inverted, so a rising edge, if you invert it, it becomes a falling edge. Nothing in the truth tables changes though, right? Because this is saying after the clock tick. If it's a falling edge trigger, we just assume the clock tick is when the clock's falling. But the truth tables are going to be exactly the same. You got homework?
Yeah.
All right, I can take that. So anything not clear about these? Yeah.
I was thinking while you're running the SR flip-flop, is usually the clock labeled when you write a triangle next to it, or is that a common?
If you've actually got a circuit, you're going to have something connected to the clock, right? And more often than not, it's just going to be called clock. But if you were doing this in a lab, you might have the output from pin 3 of a 555 connected to whatever pin the clock is on your flip-flop. So it's an input in that sense that it's got to be connected to something. But it's usually not an interesting part of, say, these state machine circuits. It's usually just coming from a line called clock. And, you know, all those homework questions that we had with these big circuits, we never even showed what was driving the clock. Right? It was just labeled clock. Because the actual clock doesn't affect any of this, right? Your clock could come from a 555, it could come from a function generator, it could come from a push button, and it doesn't change your state diagram in the end. And you never, never, never want to put the clock in your state table, the big wide table you're making. Never have a column called clock, because then you're totally going down a different path, right? All right, I can take your homework if you're... All right, so other questions about this? And we're going to be doing synthesis today, which means we're going to be working with these tables in a different way. We're going to be saying, for example, we have a JK flip-flop, and we want the next value of Q to be a 0. How do we do that? Well, we're going to set J to 0 and K to 1. Or we want the new value to be the same as the old, so we're going to set J to 0 and K to 0. We're going to work these things in kind of the opposite direction. These tables say, if this is J and this is K, what's the new value of Q? We're going to be asking the other direction. We're going to say, we want the new value of Q to be the opposite of what it was. Therefore, we want J and K to be 1. Okay, synthesis and analysis, they always go hand in hand, and it's a fundamental increase in difficulty usually to do synthesis, right? So in physics class, when I was an undergrad, right, I could watch a teacher work a physics problem. Here's a plane and the cylinder is rolling and there's a blob of jelly inside and something else, and how fast is it moving when it hits the table? And I could watch what the teacher did, and everything the teacher did made perfect sense, right? So I could analyze that, right, totally fine. But trying to do that myself, right, is totally different, and took me a long time to get to where I could do that. Same thing with coding, right? When you take coding classes, CS classes, you can see a program and somebody can explain to you what the program's doing, and that can make perfect sense, right? Analyzing the code is one thing, but then if someone says, okay, now you come up with some code to do this, right? That's a synthesis, totally different process, right? And fundamentally it seems to be harder to synthesize than to analyze. So synthesis of state machines will be a lot more work, right? But we'll go through a very well-defined process to get us to a circuit based on what we want the circuit to do. And in the end, it's going to be exactly what we were doing for analysis, but going in the opposite direction. So more work. I finished grading your labs, so let me just mention on the labs. The labs are looking really good, so keep up the good work on those. Almost all the deductions I'm making now are simply for missing pieces of the lab report, right? Which is a pretty easy thing to take care of. Just make sure you've got all the pieces. So if you're building a circuit, you got to have a circuit diagram, and you got to have part numbers and pin numbers. If it says make a sketch of the predicted waveform and compare to the observed waveform, you got to have a sketch, and you got to have something that compares it to the observed waveform, right? And it's most of the deductions I was making on this last lab were just, you know, forgetting to put in a piece that was asked for. And those are good mistakes to be making because they're easy to fix up. right? So labs look good.
Nick,
Yeah.
question. When I was trying to research for lab for experiment 3,
Yeah.
it was kind of difficult for me to figure out like exactly what you want me to find in some way.
So experiment 3, the goal was to find a actual, physical programmable device, right? So we drew some pictures of some generic PLDs, PLAs, PALs, and PROMs, right? So experiment 3, the goal was to actually find a physical device, right, online, a description of it, a data sheet, and then study that, figure out how that device gets used, and then show the fuse map and the circuitry to use that device to make a 2-bit adder. So you needed to find a data sheet, and you could do it from engrcs.com, from the component specifications, or you could Google and try to find some other PAL or PLA and get the data sheet for it, and then work with that fuse map. And then, part of choosing which device is based on, it said to look at pricing and availability and things like that. So if you wanted to buy this, where would you go? How much would it cost? How many of them do you have to buy? How long does it take for them to be available? Those kinds of things. So it was getting some experience with looking at that kind of information online, basically. Does that make sense? Okay. All right, lab 6 coming okay? Traffic lights? No? What?
We're gonna start it after class.
Okay.
We already started. We're gonna start it on Monday.
Start on Monday. All right, confidence. All right, I mostly have to leave after, well, I have class after this. And then I mostly have to leave right at 2:50. But if you've got something you're stuck on, let me know, and maybe we can talk about it at the break or something. All right, well, state machine synthesis. So I posted homework, and it's mostly variations of what we're about to do here. So let's just imagine a state machine. So here's a state A, B, C, and all right. So this is a pretty interesting state machine. Let's say it starts in state A, and I'll draw a key here. And it's got one input X, and I don't have any outputs. But basically, X is like a run input. If X is equal to 1, we're going to move from state A to state B to state C, back to A, B, C, and we're just going to keep hopping from state to state. But if X drops to a 0, we're going to stay in whatever state we're currently in. So state X is 0, that's kind of like a pause. X is 1, that's kind of like a run or a go. And it just goes from state to state to state. And we'd like to design a circuit that gets this behavior. All right, so first question, how many flip-flops do we need? Well, how many states do we have? That's an easy one. We got 3 states. Okay, so how many flip-flops do we need? 2. Because?
You could have a maximum of 4 states.
Because with 2 flip-flops, we can represent up to 4 states. We've only got 3 states here. So we can get away with 2 flip-flops. Could we use more than 2?
Depends on the flip-flop, right?
Depends somewhat on the flip-flop. It also depends on what we're going to do with these flip-flops. But we can always use more flip-flops, right? So we could use two flip-flops, and we could say 0, 0 is state A, and 0, 1 is state B, and 1, 0 is C, and 1, 1 we're just not going to use, right? And that would be the usual way to do this. But we could also use three flip-flops, and we could do something kind of quirky, like say, we're going to represent our three states like this. So if Q0 is a 1, we're in state A. If Q1 is a 1, we're in state B. If Q2, we're in state C. And we could represent 8 different states with these. We're only using 3 of those 8 possibilities. But that's a perfectly valid thing to do also. And there's actually reasons we might do this sometimes. But we're not going to do that for now. Okay, for now, let's just go with 2 flip-flops. And we'll have 1 state we don't use. So let's make a state table. And I'm going to call these Q1, Q0. Well, let me do it like this. Okay, so we got 4 possibilities. Which one of these do you want to call A? And we can pick any one we want and call it A. It makes no difference to whether we can do this or not.
There's the last.
Okay, so let's call that A. What one should we call B?
1, 0.
Okay. What about C?
0, 0.
Good, good. Okay. And we'll use this one as a don't care, right? This is basically random choice. Now, it may be helpful if you call your states something other than ABC. If I call this S00, S01, S10, it may help me keep track of what I'm doing. But I don't want us to fall in love with that particular naming pattern or that particular mapping. And I want to make sure you understand that there's no reason this has to be our so-called first state and our second state and so on. Okay? So we can basically come up with any state table that we want. Okay, well, we've got the diagram. We know what the flip-flop values are that correspond to the states. What kind of flip-flops are we going to use? So how many people want to use D flip-flops? One brave hand. How many people want to use T flip-flops? You're not going to vote, are you? And it doesn't matter because usually when you see this on a test or something, you're told what kind of flip-flops to use. But if you're building a system yourself, you can choose whatever flip-flops you want. I could make this a T flip-flop and I could make that a JK flip-flop. Right? Again, it's kind of up to you. And there's questions where you'll see, you know, use a D flip-flop and a JK flip-flop to build this machine. So let's start really simple. Let's just use D flip-flops because we know D flip-flops are pretty straightforward to work with. They have that nice simple whatever D is equal to, that's the new value of Q. So, for example, let's use 2D flip-flops. Okay, so I don't need to draw these, but I'm gonna do it anyway. So one flip-flop I'm going to call the input D0 and the output Q0. The next one I'm going to call the input and output D1 and Q1. Okay, and I'm doing this because I'm about to make that really wide table and we want those labels to correspond to something consistently. So D0, D1 will be the inputs to my flip-flops, Q's are the outputs, and here's our state table. Okay, so let's make our big wide table and we'll come back to this sheet in a moment. Alright, so looking at the state diagram, we're going to fill in present state, next state. So we know we have an input X, and we have a state, present state, and then we have a next state. Alright, so from the table I can have a 0 and be an A, 0B, 0C, 1A, 1B, 1C. So if I'm in state A and my x is a 0, I'm going to stay in A, B and C will stay where they are. If I have a 1, A will go to B, B will go to C, C will go to A. Alright, so you agree this captures what's in my diagram? Right, so I can rip this up and burn it. Okay. So we need to think about our flip-flops, and so I'm going to make another column for present state, and instead of using my names, I'm going to list the values of Q1 and Q0. So Q1, Q0. So state A is 0, 1, state B is 1, 0, state C is 0, 0. State A is 0, 1, B is 1, 0, C is 0, 0. So I'm just getting this from the present state column. So I'm just filling in from our state table. All right, next state, Q1 plus Q0 plus. So I'm going to look at the next state and just fill in what that state is in terms of Q1 and Q0. So A is 0, 1, B is 1, 0, and C is 0, 0. Alright, so I don't need my state diagram anymore. I don't need my state table. I've got everything that I'm after right here. Basically, if my input x is a 0 and my Q outputs are 1, 0, I want, after my clock tick, my Q outputs to still be 1, 0. If my input is 1 and my Q outputs are 0, then after the clock tick, I want my Q outputs to be 0, 1. So now my whole problem is, can I build a circuit which, given this and this, will result in this after the clock ticks? Well, we've only got 3 states. And usually when we write truth tables with 3 things on the left, we've got 8 rows. So we're missing 2 rows. So what are the rows that we're missing? What combinations of x, Q1, and Q0 aren't on here yet? You can go through them in order and see which one doesn't show up. This would be a good test question.
It would be 0, 1, 1, and 1, 1, 1.
Yeah. So there's 0, 0, 0, 0, 0, 1, 0, 1, 0. There's no 0, 1, 1. And there's also no 1, 1, 1. So what state do we want to go to if our input is 0 and we're in state 1, 1? We don't care, because we never expect to be in this state. And similarly, if we're in the state and x is a 1, we really don't care, because we don't expect to be in that state with our input being a 1. So we got some don't cares, which should get you happy because don't cares means simpler circuits. It means it's easier to do the K-maps. Okay, so this is the first essential piece of the synthesis process, is getting to this point in a table. And it says, given this input and given this present value of your flip-flops, what should the next value be? The next step after this depends on the kind of flip-flops you have. If we have D flip-flops, we're going to have two inputs, D1 and D0. And we can fill them in based on present state, next state. So let's just look at D1. So we have a D flip-flop, right? And we want, after the clock tick, we want this D flip-flop to output a 0. What value should we put on the D input?
0.
It's got to be a 0. And if we want the output to be a 1 after the clock tick, what value do we put on the D input? We put a 1. So again, D flip-flops look really easy because all we got to do is copy our desired state, our next state, to the corresponding D input. And since we don't care what the output is in these cases, we don't care what the D input is. All right, well, we got two D flip-flops. That's our memory. And we know that given this value of X and these values of the outputs of the flip-flops, we want logic that generates this value that we'll call D1, this value that we call D0. That's the combinational logic part. If we design circuitry that produces these and we connect these to the D inputs of the flip-flops, we're done. There's our whole state machine. So now we're back to a week 1 question. Here's a truth table. Right? These are the inputs, X, and the current values of Q, and these are the outputs we want. And you just do a product of sums or a sum of products or whatever your favorite method is. And so this is where, if you can do your states in order, 0, 0, 0, 1, 1, 0, you've got the usual ordering, but that doesn't really hurt us. We can still write equations for D1 and D0. And you could do a K-map, but let's just eyeball it. D1 looks like it should be X bar, Q1, Q0 bar, or X, Q1 bar, Q0. Right, because those are the two rows where we have a 1 for D1. And what's an equation for D0?
X bar, Q1 bar for Q0.
Cool.
And X, Q1 bar, Q0 bar.
Right, so there's a 1 right here, that's X, Q1 bar, Q0. And there's a 1 here, that's X bar, that's X, Q1 bar, Q0 bar. Right, so that's just a plain old sum of products. So what do we do with all of this? So now we can draw a circuit. So here's D1, here's D0, here's Q1. Remember, D flip-flops usually have Q and Q bar outputs, so we don't really need to go crazy with inverters because we have Q0 and we have Q0 bar, and we've got some external input X. But let's go ahead and invert it also. So there's an X bar. and I gotta move that. I'm gonna put X up here and X bar here. So I'm gonna kind of do our trick that we did before. I'm just gonna take these and run them vertically. I'm gonna label these at the bottom. I won't. I don't have room. Alright, so now you gotta make your combinational logic. So we want to take X bar and Q1 bar and Q0 and AND those together. And we want to take X and Q1 bar and Q0 bar and AND those together. And then OR those. And that should be D1. So we're going to take that, bring it back to D1. And then D0 is going to be X bar, Q1, Q0 bar, and then X Q1 bar Q0. So there's X Q1 bar Q0. And those, and OR those together, and that should be D0. So I'm going to take that and run it over to D0. And then there's a clock on these, and the clocks always get tied together. So there's our external clock. There's your state machine. So it's a lot of steps, but it's a lot of things to do, but it's really only just a few steps. But each of those steps takes a lot of things to do, right? But basically you decide how many states you have, decide how many flip-flops you're going to use, decide or have been told what kind of flip-flops, make a state assignment table, and then work on your state transition table based on inputs and present state. What should the next state be? Translate that into flip-flop output values, and then figure out what the inputs of the flip-flops have to be to make this transition happen from present state to next state. Then write equations for those flip-flop inputs, and then basically design a circuit that implements those inputs, connect them to the inputs, tie your clocks together, there's your whole state machine. See, it only takes 20 seconds to describe, but it's a good like 45 minutes to do some of these. And the first time it could take you an hour or more to do one of these, because it's a process to learn. All right, let's do one more. Let's use some different flip-flops. And then we'll take a break, and then you can work on these on the board. So let's see. And I'm going to call my states something more traditional here. State 00, state 01, state 10, state 11. And let's make this a more machine. So how would you describe what this machine is doing? If you want to just summarize all of the individual transitions here, what's the 1 or 2 sentence description of what this machine does?
Counts up and then when it gets to 0, it counts down.
Yeah, if it has a 1, it basically counts up. If it has a 0 on the input, it basically counts down. And what else? How is it different from a plain old binary up counter or down counter?
If it gets to the end, it counts 1 and loops there.
If it gets to the end, it loops there, right? An up counter, once it got to 3, it would go back to 0. But this one, once it gets to 3, it just stays at 3. And if you're counting down, once it gets to 0, it just stays at 0. So it doesn't roll over. And what is the output telling us?
When it's looping, it's a 1.
Yeah, the output's telling us that it's at one extreme or the other. It's either stuck at the high value or it's stuck at the low value. All right, excellent. So we don't need to know what the machine is doing. All we need is a state diagram, right? But sometimes it's useful to think about what it's actually doing. But it's not a necessary step. All right, so 4 states, how many flip-flops should we use? Let's use 2 flip-flops. If we use 4 flip-flops, that's 16 rows times 2 for our input. That's going to be 32 rows in our state diagram. But most of them are going to be don't cares. And it's actually going to end up being easier to implement the circuitry, usually. But it's a big table. So let's do 2 flip-flops. Okay, we're going to use JK flip-flops. So use 2 JK flip-flops. And I'm going to name my states based on the value of the flip-flop outputs. To help minimize the chance of my getting confused. And in fact, if my states were called A, B, C, D, I would probably just rename them to 0, 0, 0, 1, 1, 0, 1, 1, and then name them back at the end or something. All right, well, we have 1 input, we have 4 possible states. So let's start our state transition table. So here's X, here's our present state. All right, 4 possible states, 2 possible inputs. So 8 rows in our transition table. And then what do I want to put in the next column?
Next state.
Sounds good. And here we just read from the diagram. So if we've got a 0, if we're in 0, 0, we should stay. If we're in 0, 1, we should go to 0, 0. If we're in 1, 0, we should go to state 0, 1. If we're in 1, 1, we should go to 1, 0. And a 1 is counting up, so 0, 0 goes to 0, 1, 0, 1 to 1, 0, 1, 0 to 1, 1, and 1, 1 stays in 1, 1. All right, what goes next? Yeah, let's put in the cues because we can't really work with names like this. Let's put in the cues. So let's write present state, and we're going to use Q1, Q0. So now I'm just filling in from our state table. S00 is a 00, and I don't even need to look at my state table because the way we name the states, this is just the subscript. So that's pretty straightforward. And then we want the next state, Q1 plus, Q0 plus, and that comes from the next state column. So 0, 0, 0, 0, etc. We do have an output in this case. Let's go ahead and throw that in right here so we can toss our state diagram. So let's add Z. So when is Z equal to 1? Which states? Right, just 0, 0, and 1, 1. It's a Moore machine, so it depends only on the state. So anytime our present state is 0, 0, we want our output to be a 1. Right, and I'll put in parentheses PS to remind you this is based on the present state. All right, now for the fun part. So these are JK flip-flops. The value of a JK flip-flop after a clock tick depends on two things, value of J, value of K. So let's make a column for J1 and K1. And let's make another column for J0 and K0. Okay, only think about flip-flop 1 for a moment. So we're only interested in Q1 and Q1 plus and J1 and K1. And let's remind ourselves what a JK flip-flop does. Okay, let's just look at the first row for Q1. Q1 is currently a 0. After the next clock tick, we want it to be a 0. What value should we set for J1, K1? We're trying to go from a 0 to a 0. 0, 1. Is there any other value we could have used?
0, 0.
We could also use 0, 0 because 0, 0 says don't change, right? And since it's already a 0, if we put in 0, 0, it'll also change. So this is 0, 1 or 0, 0. Well, it's clear J1 has to be a 0, but K1 apparently doesn't matter. Whether it's a 0 or a 1, it's still going to end up with a 0 in the output.
Does that mean you put don't care?
So we put a don't care for K1. So this is actually going to be 0, don't care. All right, well, second row, Q is a 0. We want the new value of Q to be a 0. That's the case we just did. So this is also going to be a 0, don't care. And while we're at it, are there any other cases where we're trying to change from a 0 to a 0, just looking at Q1? Yeah, here's a 0, we're going to a 0. So J1, K1 are also 0, don't care. And while we're here, what if we do look at Q0? Any cases where Q0 is currently a 0 and we want it to be a 0 after the clock tick? Yeah, definitely that first row. So that's a 0, don't care. And I think that's the only one.
The third row? Oh, wait.
Yeah, 0 to 1. Okay, well, we got the first two rows filled in. Let's go to the third one. Q1 is a 1. We want Q1 to become a 0. So what are the values for J and K to change from a 1 to a 0? 0 and 1. Because anytime the inputs are 0, 1, the next value of Q is a 0. Any other values we could have set on J and K to get that same result? Yeah, so if we made this a 1, 1, that would say toggle. And since the current value is a 1, after the clock tick, it would toggle and become a 0. So this is an example of don't care or 1. J1 is don't care, K1 is a 1. So this is why JKs are nice to design with, because we always have some don't cares in our truth table. We have twice as many inputs to set up to the flip-flops, but we're going to have probably simpler equations. Alright, and so anywhere there's a 1 going to a 0, we can write dash 1. So 1 going to a 0, nothing else for Q1. For Q0, here's a 1 going to a 0. So that's a dash 1. Here's a 1 going to a 0. Here's a 1 going to a 0. And I think that's it. Oh good, I am recording. Alright, got the idea? And obviously after you've done this a few times, right, it's not going to matter what we're calling our states, what our circuit looks like, what color ink we're using. If we're working with JK flip-flops and we're trying to go from a 0 to a 0, we're always going to write down 0 dash, right? So you can make a little table that says if this is my current state and this is my next state, what should J and K be? And you don't have to go through this mental process of, well, it could be this or it could be that, right? But I want you to go through that process a few times initially and make sure that you understand it, rather than just having a table that you look something up in. Because eventually you forget what table you're using for what, and it makes no sense, right? If you understand why we're writing a 0 dash or a dash 1, you can't go wrong, okay? But then on your note sheet, you can start putting down some reminders. All right, want to go from a 1 to a 1, what are our options? Current state's a 1, new state's going to output a 1. So we could do 0, 0, which says don't change. You're a 1, stay a 1. Or 1, 0. So that's either a 0 or a 1 for J and a 0 for K. So anytime there's a 1, 1, that's a dash 0. So this is a dash 0. That's a dash 0. And for Q0, that's a dash 0. And I think that's all we got. All right, one case left. Current value is a 0. New value should be a 1. So what are the possibilities? 1, 1, which says toggle. Or 0, 1, which says set. Sorry, 1, 0. 1, 0, which says set the output to a 1. So this is a 1 and a don't care. So 0 to 1, 1 don't care. 0 to 1, 1 don't care. 0 to 1, 0 to 1, 1 don't care. All right, let me clean up this table to highlight what we actually care about. We care about the input and the present state. Bless you. And we're going to build circuitry to generate J1, K1, J0, and K0. And this looks like 0 dash 0 dash 0 dash dash 1 dash 1 1 dash dash 0 dash 1, and then 0 dash 1 dash 1 dash dash 1, and then dash 0 dash 0 dash 0 and 1 dash, and then we also want our output Z. Alright, so there's a truth table problem. And this is a total joy to work with. So here's X, Q1, Q0. This is for J1. So for J1, where are our ones? 1, 0, 1. And our don't cares are over here and over here. And so that's got a pretty easy cover. So J1 equals X. Let me do that. So X Q0. So if X is 1 and Q0 is 1, we want an output of 1, and anything else we don't care, we have a 0. And so on, right? So K1 is going to have a single 1 and some don't cares. J0 is going to have 3 ones, but everything else is a don't care. So what's our equation for J0? It's pretty straightforward. It's only got one value that has to be 0. So if all of these don't cares were 1s, this is just the OR of X, Q1, Q0. And K0 could be 1 everywhere except this. This is just a NAND. So if you do the K-maps for these, they come out pretty straightforward. And this looks like an XOR of 3 variables to me. No, it doesn't. It looks simpler than that. This looks like an XOR of X and Q0. Or Q1, Q0. So more work with JK, right? More columns to fill in. Same number of rows based on flip-flops and number of inputs. More columns to fill out. More equations to write, but your equations are probably going to come out pretty simple because we have all these don't cares. And like I say, usually you're going to be told what kind of flip-flops to use. Some of the homework questions show you a state diagram, and then part A says use D flip-flops, part B says use T flip-flops, part C says use JK flip-flops. Right? But if you get a question like that, all of this is exactly the same up through here. Right? None of this has to do with what type of flip-flops we have. The only thing that comes into play when we do the type of flip-flops is the inputs to the flip-flops. So if you've done this for JK, now you want to do it for T, you just make a new column, T1, T0, and you fill those in based on input, present state, next state. And then if you want to do it for Ds, you just make a new column for D1, D0. All right, it's really wide sheets of paper, good eraser, nice sharp pencil. And, you know, it's not unheard of to tape sheets of paper together to make them wider because it really helps. All right, let's do a 5-minute break, and then I'll have you go to the board and we can start doing these in groups and make sure we've got this process down.